All right, picking up where we left off yesterday. So we've started into my other source of learning, C++, which I think is a little more detailed, has a lot more information in it. And we are currently going through just the simple introduction of this material. So we got Learn C++, or cpp.com on the right side, and the my text editor VS Code on the left side of the screen here. um, and there's a lot of reading to do in this. I know these videos are probably quite boring right now. Hopefully that'll change over time, but until I get this learned, it is the way it is. I mainly do this and stuff just to share my journey of learning C++ and understanding it. It also helps me to kind of stay awake because I used to, when I did this without making these videos, I would read through this stuff and I would literally be falling asleep on my desk right here in my chair. So making these videos actually helps me to also stay awake because I'm talking and being more active while learning this stuff. So we left off with assembly languages, which is pretty much um, machine code, machine language, which let's get started into this. Machine language instructions like uh, ones and zeros are ideal for a CPU, but difficult for humans to understand. And yes, that's true. You could study it and probably get it to where you can understand it, but um, depends on what you are trying to accomplish. So I'm currently not in that focus of trying to learn what different sets of ones and zeros mean. I'm only trying to learn how to write the code itself and let the compiler translate it for me. Since programs, at least historically, have been written and maintained by humans, it makes sense that programming languages should be designed with human needs in mind. An assembly language, often called assembly for short, is a programming language that essentially functions as more human readable machine language. Here is the same instructions as in x86 assembly language, MOVAL. So this is pretty much looks like an assembly language code, but I'm not familiar with it. So optional reading right here. This instructions illustrates many of the capabilities that make assembly more readable than machine language. The operation, what the instruction does, is identified by short numeric, typically a 3 to 5 letter name. Move is easily understood to be a numeric for move. So we just basically shrunk it down, cut one letter off the end of it. Um, yeah, which is an operation that copies bits from one location to another. So basically taking um, a set of instructions and stuff. So take this right here from the CPU, move it to the memory, or move it to the storage, or send it out to the server and stuff to request information back, or whatever it may be. Registers, fast memory locations that are part of the CPU itself, are accessed by a human. AL is the name for the specific register on a x86 CPU. Numbers can be specified in more convenient format. Assembly language typically supports both decimal numbers, etc., like 97, or hexadecimal numbers like 0x86 or 61. Sorry. It's fairly easy to understand that the assembly instructions that we've mentioned here, the move, human, or whatever this is, fast, yeah. I know I just read it and stuff, but um, trying to get that fastly understood just by reading the text right there. Uh, it's still complicated for me. Copy hexadecimal number such and such into an AL CPU register. Okay, so I don't fully understand what I just read there. I know that it's pretty much telling me, trying to explain to me what this line of code right here would be. Um, but since I haven't studied it very well, it's pretty new to me, and even reading this little part right here doesn't fully make sense to me. So, since CPUs don't understand assembly language, assembly programs must be translated into machine language before they can be executed. This translation is done by a program called an assembler. So it sounds like an assembler is the same thing as a compiler. Uh, when you write code like this, what you're writing is something you understand, and then an assembler will take that and turn it into machine language so that or machine code so that the computer, or whatever it may be, can understand it via assembler. So, um, because each assembly language instructions is typically designed to mirror an equivalent machine language instruction, the translation process is typically straightforward. So it sounds like assembly language is pretty well the same thing as any code you would write, where you have the code you write yourself, you understand what it is. Assembly language the same way. And then for like C++, we have a compiler that translates it from the code that I understand to a language that the computer understands, or whatever device you're using. But when it comes to assembly language, it looks like it's an assembler that does the same thing, translates it from what you understand to something that the computer would understand. Just like each CPU family has its own language, machine language, each CPU family also has its own assembly language, which is designed to be assembled into machine language for that same CPU family. This means it seems like there is a lot to have to deal with a program. If you want the program of any sort that you understand to be written and be able to work on any computer by anybody, so any program out there, you're going to have to make sure that it can be translated to a language that can be understood by that type of computer. Since CPU families and stuff understand code differently, that's probably why some computers won't run certain programs and others will. Um, which then is why also when you look at the details of programs, they tell you what is required in order for that program to work properly. If that makes any sense. It kind of does to me, but I'm still working on it. This means that there are many different assembly languages, although conceptually similar. Different assembly languages support different instructions, use different naming conventions, etc., which is pretty much what I just said. So we got an introduction here to low-level languages. Machine languages and assembly languages are considered low-level languages. So ones and zeros, or something you would type into a text editor to give instructions. I do know that you would have to, so most of the libraries out there for C++ contain code from C++ to do certain things. You would have to mix, it looks like, assembly language with whatever code you're working with and stuff if you want your code to activate things in your computer. I've read that for the most part you can get a program to run, but you can't activate anything inside the computer without some sort of assembly language. Assembly language is what gives you the access to be able to activate your graphics card, your Ethernet or internet, storage device, that sort of stuff. Uh, so yeah, for me, it's a lot to take in because there's a lot going on right here. And that's probably why there's so many different people in so many different fields that understand it. And then a company would have so many different people to write specific code. One person to write assembly code, one person to write translators, one person uh, to write an actual program, sort of thing, so forth and so on. But yeah, let's finish up with this. In other words, the programming language itself is tailored to a specific instruction set architecture, which would be a specific machine. If another machine doesn't have the same kind of architecture to it and stuff, then you're going to have to write another program on top of that so that it can be translated based on the architecture of the machine itself, of the computer itself, or the device. Low-level languages have a number and notable downside. Programs written in low-level languages are portable. Since a low-level language is tailored to a specific instruction set architecture, the program written in the language uh, are two. The programs written in languages are two. Okay, so I didn't really read that sentence properly. Programs written in a low-level language are portable. Since low-level language is tailored to a specific instruction set architecture, the programs written in the language are too. Okay, so yeah, that pretty much means that everything you write and stuff, when I write in code for myself, I have a compiler and the programs, everything are set up for my specific computer. Um, and when you go to write code, if you have a different kind of computer, your programs, compilers, everything you have is pretty much designed for your computer. So when you write code and you send it to me to do whatever with, run it. If it's a game, play the game. If it's not set up for both your computer and my computer, then it may not work on my computer at all, and vice versa. Writing a program in a low-level language requires detailed knowledge of the architecture itself, so you have to know um, about all the different types of computers out there, which is probably why the study of computer science exists, not to mention the study of the hardware. And I mean, in my mind right now, I am seeing a vast universe of millions of options in this, depending on a computer. Now, if another company comes out with another set of computers with another set of languages, all that sorts of stuff, then every program out there, in order for it to run on that computer right there, is going to have to be rewritten so it'll work on that specific type of computer. Kind of like with the languages and stuff. If you write a program to where it's written in English, then only people that can understand English are going to be able to read it. Um, and that doesn't even include people that may be blind or hearing impaired. Uh, if you want them to be able to understand it, then you got to write it to where it can either voice it so they can hear it, or in Braille so they can read it off of paper when it prints out, so forth and so on. That's why I'm sitting there saying that a vast universe, because there's infinite possibilities and stuff. And if you want to reach out to everybody with your program to allow everybody to be able to access it, then you got a lot of work ahead of you. It sounds like. Same for me though. So for instance, let's keep reading this. The instructions such and such requires knowing that AL refers to CPU register available on a specific platform and understanding how to work with the register on different architectures. This register might be named something different, have different limitations, or not exist at all. Low-level languages are hard to understand while individual assembly instructions can be quite understandable. It can still be hard to deduce what a section of assembly code is actually doing, and since assembly programs require many instructions to do even simple tasks, they tend to be quite long. It's hard to write assembly programs of significant complexity because the language only provides primitive capabilities. The programmer is left to implement everything they need themselves. The primary benefit of low-level languages is they are fast. Assembly is still used today when there is sections of code that are performance critical, and it's also used in a few other cases, one of which we'll discuss in a moment. So yeah, with all the different types of devices out there, all the different types of computers out there, each one of them can end up like Android, iPhone, Intel, Ryzen. Uh, what else is there? Uh, there's a vast many different types of computers out there. I don't know them all, but it sounds like if you want your program to run on any device, you're gonna have to study all of them and understand the machine code and then write programs to where it'll translate the architecture of whatever the user is using. Which is probably why it's kind of difficult for some people to do certain things on websites or applications or programs or games. And that's just because your computer is not capable of understanding the code that's being run through your computer. Which is also why it requires teams of people to write the code. Because if you want it done quickly and you want the game to start working so other people can play it, or programs so that people can use it or whatever and stuff, then you're going to have to, especially on phones. I know that the majority of it out there and stuff is either an iPhone or an Android. I know that the majority of it out there for computer, laptop. I don't know about tablets. I don't know what they use. They probably do use pretty much the same kind of a chipset for that. But and then you have the variety of different chipsets per Intel, per uh, Ryzen, so forth and so on. Okay, introduction to high-level languages. So now we're getting into two different categories of languages. To address many of the above downsides, new high-level languages such as C, C++, Partial, and later languages such as JavaScript, Perl were developed. So it sounds like C, C++. In fact, many of your languages out there are more of high-level languages, where low-level languages are the assembly code, or the assembly languages, compilers, assemblers, so forth and so on. It sounds like to me. Here's the same instructions as above. So the same set of instructions that we had right here with the move AL 061H. The same instructions, it would be from assembly language to C++, or C would be A equals 97, or A is set to 97. Much like assembly programs, which must be assembled to machine language, programs written in high-level language must be translated into machine language before they can be run. There are two primary ways this is done: compiling and interpreting, which is compile time and I believe runtime, but I'm not sure about that. C++ programs are usually compiled. A compiler is a program or a collection of programs that reads the source code of one language, usually a high-level language, and translates it into another language, usually a low-level language. For example, C++ compiler translates C++ source code into machine code. There's some optional reading right here. Most C++ compilers can also be configured to generate assembly code. This is useful when a programmer wants to see what specific instructions the compiler is generating for a section of the program. So they write a program, and they also write they understand assembly language. So they also write a code to basically print out what the computer or PC would be seeing in ones and zeros. So they probably even understand the machine language as well as the program they're writing, or the code that they're writing, which I think would be hard enough, and that'd probably take a lot of studying to figure that out. Continuing on here, the machine code outputs output by the compiler can then be packaged into executable file containing machine language code instructions that can distribute to others and launched by the operating system. Notably, running the executable file does not require the compiler to be installed. Yeah, because the compiler is already translated it into machine code, and therefore you're not passing on the program, you're passing on uh, the executable code, which has already been translated, um, if I'm understanding that correctly. In the beginning, compilers were primitive and produced slow, unoptimized assembly or machine code. However, over the years, compilers have become very good at producing fast, optimized code, and in some cases can be a better job than humans can. Here is a simple representation of the compiler process. So you get the high-level language C++, compiled by the compiler, then produced into executable code or a file, which is where we get the exe from. So your C++ program file .cpp, and then behind the scenes something that you have to install in order for this to run. But what gets passed on is you wrote the program, the compiler translates it into an executable code, and now what you're passing on is that executable code when you're having somebody else run your program, play your game, so forth and so on. So this is the part right here. I can't really. Yeah. Okay, we're not going to do that. And then, so when somebody gets the executable code, they run it. The hardware, it's run on their hardware, produces program results, games, uh, calculators, whatever it may be, software. Alternatively, an interpreter is a program that directly executes the instructions in the same code without requiring them to be compiled. The first interpreters tend to be more flexible than compilers, but are less efficient when running programs because the interpreter process needs to be done every time the program is run. Um, so yes, I believe most computers nowadays probably have that built into them to where they have the ability to uh, interpret whatever code is installed onto the computer. So when you install it and stuff, it's probably translating it into something that your computer can understand. So that's like 4 different levels. You wrote the program, now you're turning it into a file that can be executed and run. And then it's getting downloaded by other people to be run on theirs, but when it gets downloaded, it gets interpreted and then translated into something that their computer would understand. So you got a lot of different, I mean, there's 6 right here, but I imagine if you had yours right here and then 6 people taking this right here in, yours is getting translated, somebody else is getting translated differently, somebody else is getting translated differently, and you have something in right here with those operating systems that are, and that's confusing and quite hard to understand. I get it a little bit, but not fully. Here's a simpler representation of the interpretation process. You write the code, something interprets it. Um, let's see, high-level language, which would be C++, interpreted, which would be the compiler. Hardware activated, which would be whatever my computer understands, which is translated from the compiler, um, and then the program results. And I may not be understanding that correctly, so feel free to um, leave comments on that in the comments if you would like. Optional reading here, a good comparison of the advantages of compilers versus interpreters can be found here. So it doesn't sound like, and I wouldn't really think so, compilers and interpreters not being the same. No, a compiler translates it into whatever your machine understands, which you have to have the proper compiler for that, and an interpreter can translate that uh, into something your machine would understand. But if you're not using my same machine, the process right here of compiler interpreter for me would be done in one simple step. Since the compiler is designed for my PC but not for yours, you would also have the interpreter to translate it from what my compiler translated it for my machine. And yeah, wow, that's confusing quick. Uh, I can imagine you would lose an auditorium of people really fast with that, unless you understood it really well and can just simply explain it to where they would understand it. But that might be kind of difficult depending on everybody, how everybody. I mean, it's the same way for people and stuff. You can say something and explain something one way to a person and stuff, but they don't understand what you're saying because their mind works differently than what yours does. You get a group of 10 people and stuff, and everybody's mind works differently, and you may have to sit there and explain it 10 different ways for each person to understand it because all their minds work differently. So you are doing pretty much the high level language yourself in this example or analogy. You are doing the compiling work yourself to where you understand it yourself. It's the work that you did to understand it, and now you're having to interpret it to the hardware, which is the 10 different people. So then they understand it and have the results of what they can do. That's about the best way I can explain that. Like I said, I may be far off from that, and it's fine. Um, Morally, the idea of discovering it and understanding that something like that might be possible. Getting the details down will have to come later. Most high-level languages can be either compiled or interpreted. Traditionally, high-level languages like C and C++, Parcel are compiled, whereas scripting languages like Perl and JavaScript tend to be interpreted. Some languages like Java use a mix of two. We'll explore C++ compilers in more detail shortly. The benefits of high-level languages. Um, High-level languages are named as such because they provide a high level of abstraction from the underlying architecture. Consider the instructions A is set to 97 and then declared with the semicolon. This instruction lets us store the value of 97, whereas in somewhere in memory without needing to know exactly where the value will be placed, or what specific machine code instructions are needed by the CPU to store that value. So yes, the compiler also, or there's a process also where when you run your program and stuff, the first thing that's happening is the CPU is getting the information from my screen, or the instructions that I've typed up. So I'm typing, these instructions are going to the CPU, then going to the monitor, and then when I hit the run button, then there's a set of instructions going from the monitor back to the CPU, and then at that point in time, the instructions are also being translated to where every piece of code needs to go. So we need to create a storage spot in the storage room for this file to sit. Then we need to use the RAM and stuff to store some of this information until we get everything set up. So let's go ahead and make this block right here. Yeah, that gets confusing quite quick. Whew. Yeah. A lot of processes going on and stuff between one spot and another, and all the work that came before me even to understand how all this stuff worked to make what is currently possible. Years worth of study by many people. So, where did I leave off here? This instruction stores the value 97 somewhere in memory. Yep, I already read that part. In fact, there is nothing platform specific about this instruction at all. The compiler does all the work to figure out how C++ instructions translate into platform specific machine code. High level languages allow programmers to write programs without knowing much about the platform, which would be someone like me. Um, I'm able to write programs and stuff, even though I don't even understand that part right there, onto platforms that I don't understand, using compilers that I don't understand. uh, so that the computer that I don't fully understand can do whatever it does. A lot of not understanding and not knowing what's happening behind the scenes. Give me a car, and that's a completely different story. Is it not only makes programs easier to write, it also makes them significantly more portable. If we're careful, we can write a single C++ that will compile on every platform that's C++ compiler that has a C++ compiler. A program that is designed to run on multiple platforms is said to be cross-platform. So you got the C++ language, and you got a compiler for x86, then you got another compiler for PowerCP hardware, then you got another compiler for MIPS hardware, which then is turned into an executable file for all three of those. So there's a lot of compiling, a lot of interpreting going on just to make a program when you go to download it and run it. Games, applications, so forth, so on. So when you wonder why it takes so long and stuff, well, if you had to do the work yourself, I guarantee it'd probably take closer to a month, and that's if you understood it. If you didn't understand it, would take much longer than that. Because can you imagine and stuff? Yeah, I got this game here. If you want to try it out, sure, what is it? And they give you like a huge book with a bunch of ones and zeros that you have to type into your computer, save it to a file, but you have to type it in a way that your machine would understand, and so it's going to take you a month to do that. And that's if you understand what send it. Most of us don't have that kind of patience, don't have that kind of time, and we're just, for me and stuff, I'm just grateful that all the people before me were able to understand this stuff and make it so that this becomes a lot easier for me. For advanced readers, the following is a particular list of things that can inhabit the portability of your C++ code. Many programming systems, such as Microsoft Windows, offer platform-specific compatibilities that you can use in your code. These can make it much easier to write a program for a specific operating system or provide deeper integration with the operating system than would otherwise be possible. Many third-party libraries are often available for certain platforms. If you use one of these, you will be limited to the platform for which that library is supported. So yes, even though you might be learning C++, doesn't mean you can use all the libraries out there. Um, Especially if that library was built by somebody with a different computer than what you have. Uh, you might be able to download the library, but it doesn't mean you're going to be able to use it. So remember that if a library is not working properly. Some compilers support compile specific extensions which are uh, capabilities. I don't understand why it's typed like that, but which are, unless I'm reading it wrong, I could be reading it wrong, which are capabilities that are only available in that compiler. If you use these, your program won't be able to compile by other compilers that don't support the same extensions without modifications. We'll talk more about these later once we've installed a compiler. In certain cases, the C++ language allows the compiler to determine how something should behave. We discussed this further in lesson 1.6, initialized variables and defined behaviors under implementations defined behaviors. Um, so yes, as you can see already, this is stuff right here that you wouldn't learn in W3 School's website. It's a very basic thing. This right here is getting a lot deeper into understanding what's going on behind the scenes. You want to write a program and stuff, and then next thing you know, so you studied on W3 Schools or you studied on uh, freecodecamp.org, and you start writing a program and stuff, and next thing you know, you want your friend to try it out. Well, you have a Windows operating system where he has a Mac operating system. So he goes to plug it in and stuff, and he can't get it to work. And you are both sitting there for hours trying to figure out why it's not working. Well, this in-depth understanding of it would explain to you why it won't work. And it's because when you built the program was specifically built, compiled, and translated for your machine to understand it. So if you want his machine, a Mac, to understand it, you're going to have to add in the ability for it to be interpreted by a Mac machine. Now, or he can download a program and stuff that will translate it from a Windows operating system to a Mac operating system. We also got Linux out there too, so there's that one as well. Android, iOS. So there's a huge, but I mean, if you just studied those and stuff, you made the program and you don't understand why it won't work, this is so much more detailed into understanding what's going on behind the scenes because you didn't even know that behind the scenes stuff existed prior to this. Moving on, if you if you're only targeting a single platform, your computer, the portability may not matter that much. So if you're just planning on running it on your computer alone, nobody else's, then yes, the portability won't matter. But many applications these days target multiple platforms in order to widen their reach. So you want it to be able to be played by anybody running any kind of operating system. For example, a mobile app will probably want to target both iOS and Android. Yes, for a while there and stuff, when smartphones came out, if you wanted to play a game, you only had the option of, and it still kind of exists right now, you only have the option of playing games that are capable of being read and understood by an Apple phone or iOS. But your friend has an Android and he's playing a game that looks really cool. Unfortunately, you can't play it without either having an Android or having some kind of program that will translate that program that he's got or his app onto something an iPhone would understand. Now, companies are getting smarter and are making it to where both sides can use it because pretty much it's a 50-50 split between, didn't mean to do that, a 50-50 split between uh, Android and iPhone out there. There used to be a lot more phones out there. Nokia, um, I think BlackBerry used to. I don't remember. I don't think that used to be Android. I don't remember, but yeah. So, um, but yeah. Anyways, moving on. Um, let's see. Where was I? Many applications. For example, yep. Okay, so even if a even if portability doesn't seem useful initially, many applications that initialize target a single platform decide to port to another platform. So PC to Mac, after seeing some level of success and interest, if you don't start with portability in mind, it will be more work to make it portable. So that basically what it's saying, if you don't keep the idea in mind and stuff, that yes, it'll work on your system, but will work on another operating system. If you don't keep that in mind and stuff at the start of your code will be much more difficult to write because you're going to have to make a bunch of adjustments so that it'll be readable by different operating systems. I don't have a whole lot more here to go, but I don't want to make this video too much longer. So I think we'll just pick up in the next video and stuff, just underneath this right here, the for advanced readers part in the next video. Um, uh, hmm. Yeah, I think we'll pick this up in the next video and stuff because we got a lot more to go through. Um, there's, I think, 10 to 12 sections just for this understanding. And all this is doing is just explaining what's going on behind the scenes. Yes, I could teach you how to write code, but if you don't understand what's going on behind the scenes, then you won't understand why it's not working on other platforms, on other machines, on phones, so forth and so on. And it may get frustrating and irritating, and then you may end up quitting just because you don't understand it. Well, this is, like I said, still basic stuff, but a much more depth detail about it. So I think I'll stop the video right there. Again, if you like the video, hit the like button. I understand this stuff is kind of boring and everything, but like I said, when you go to program stuff and you start making a program and it doesn't work on your machine, or it behaves differently on your machine than what it does your friend's machine, understanding why can be a huge key into trying to let the developers know, hey, this works on his machine, but not my machine. Is it set up for my machine? I have a PC here that's running Intel with Windows operating system on it, and they could look at that and say, nope, we forgot about that one. We made it for Mac, we made it for Linux, and we made it for Windows 10, but not Windows 11. So we need to add code in there so it'll work on Windows 11 as well, or add code in there that'll work on Intel as well, so forth and so on. Because I mean, yeah, it's very easy for a company, even with a group of people, to forget something small as that. So hope you enjoyed the video. I know it's probably kind of boring going through this stuff right now, but like I said, when I was going through this before and stuff, I would sit there and all of a sudden just doze off like this, and getting through this material took 2, if not 3 times longer what it's going to currently take me making these videos and sharing them, even if nobody watches them. I'm not worried about people watching them. I'm really worried about me understanding it, reading it, and learning it. So, I'm just sharing a journey. That'll be it for this video, and I'll come back in a little bit for finishing this up and moving on to the next section. See you next time.